Good evening. Welcome to the Gulf of Maine Research Institute. I think I see a lot of familiar faces in the crowd, so I suspect that most of you have been here before. My name is Jonathan Lavery. I'm the director of, or the chief community officer here, so I run our community program. As you know, the Gulf of Maine Research Institute is a marine research lab, and we study the ecosystem of the Gulf of Maine. We have research scientists who try to understand what's happening out there and how it all connects, including how humans interact with the ecosystem and the impact that we have on that ecosystem and vice versa. We do an education program. You're sitting in a glorious lab where we get 5th and 6th graders here from all over the state to teach them about science. The program that I run, our community program, we interact and work with fishing communities around the Gulf of Maine as they adapt to changes in the markets, in the ecosystem, and in management. But we're here to hear John Cannon speak. Our lecture series this spring is on motion in the ocean, and we're talking about the dynamics of the ocean ecosystem, and particularly as it impacts our coastline. John is the Marine Program Manager at the National Weather Service up here in Gray. Those of you who know, it's up near Pineland, and you see the big dome when you drive by. And I just learned that twice a day they launch weather balloons. Who knew that they will launch weather balloons there twice a day? It's totally cool. Yeah, 7 o'clock in the morning and 7 o'clock in the evening. I'll be there. I think that sounds really cool. He's interested in coastal prediction, observation, and evaluation of tropical and intense extratropical storms affecting mariners and shoreline residents, emergency responders, and many other stakeholders within the community. Focuses both on research and operational partnerships for improved customer service of our commerce, military, and public sectors. Resources for these marine efforts are leveraged through serving on numerous local, regional, and national teams in the government and private sectors to benefit the commercial fisheries industry and the public. Having lived in a residence along the vulnerable and changing shoreline in southern Maine, John has a deep appreciation and understanding of storm processes occurring in the coastal waters, surf zone, and along eroding beaches. He's a graduate of the University of New York at Oswego, where marine services focused on lake effect storms, not something that we have to deal with very much, but they do there. And other hazards along in the Great Lakes region. So join me in welcoming John. Thank you.
I don't do any of that. I was just walking by tonight looking for a place to visit. I speak fairly loudly, so I should be okay. If I'm a little low or whatnot, let me know. I've also been told I'm not allowed to move within this far of the podium and all that, so I'm going to be anchored and chained here. I'm a meteorologist with the National Weather Service, a true life one. I really wanted to conjure up a storm tonight to make this really be, what it's all about. Last Thursday night, a week ago, we had the 16th highest tide ever in Portland, Maine, in over 100 years. So not a lot of people know about that. One, it happened at night when the water comes up and then goes back down. Nobody knows about it. It's not documented. And two, there weren't very big waves. And the Weather Service and NOAA has really been focusing on water level and flood stages for the ocean for quite a while, but I'm going to be trying to hone in on waves tonight and how waves cause erosion and how it causes coastal flooding and damage to infrastructure and whatnot. So it's a beautiful night out there, so I'm not going to hold you to too much time. We'll get through this pretty quickly. We'll answer questions. Some people already had a lecture series thing at lunch, so I've got a lot of pretty pictures, which is good, so your mind can go to mush a little bit. And I put this one big, long equation in there because it sounded so scientific that it was a lecture series. So anyways, to get onward here, we have many partnerships. This is the 10th anniversary of the Patriot State storm. I live down in Saco, Maine, which you'll see a lot of photos from Saco. I didn't steal them. I took a lot of them myself, although I do like to steal photos. So this was a big storm 10 years ago. 30-foot waves offshore, big tides. So we're going to be, this is the National Weather Service, and I'm working an overnight shift. Some of these photos are a little personalized, but am I outside the range already? I got to get back in here. Sunrise, this is April 15th, about 10 years ago. Everything is fine. The weather's beautiful. Red sky in morning. Uh-oh, that's right. That's not a good thing. I just realized that. So 24 hours later, a lot of damage to infrastructure, some homes lost in Saco. That's an infrared satellite photograph showing a storm developing off the mid-Atlantic coast, pretty much near New York City, and coming in from in the ocean. It deepened incredibly fast. That's called bombogenesis, when we have these low-pressure systems really just strengthen really fast, really quickly. We also had 5 to 8 inches of rain, which is not thought about and discussed much during the storm, but that does have an effect on flooding of estuaries, where all the fresh water is coming out and the tidal surge is coming in, the salt water is coming in. You can really have some enhanced flooding in some areas. So we also lost a buoy, which is not too uncommon. The Portland buoy, 44007, resides right out here. That ended up near the Isle of Shoals because of the extreme storm we had. Most of the time when we lose a buoy off its mooring, it ends up in Spain. So this is a pretty good deal. It does. The currents take it to Spain. So we got to send some boat over there to. So this is my home. Drive home from the midnight shift. Trees and wires down. Driving over wires. Driving over tree stumps. This is Ocean Park down in Old Orchard Beach. If you know the area, it's really beautiful down there. And quite a midnight shift. And then when you're an emergency, considered emergency employee, when you're all done at work after 20 hours, you got to go home and deal with your own things. And that's the type of work we do. But for some reason, we love it. The bigger the storm, the better. Here's a Patriot Day storm at 9 o'clock in the morning. High tide's at 10:30. I'm in a patrol car with the emergency manager from Saco, Steve Bucavalis, and there's already waves crashing over the roadway at this point. So we're still an hour and a half from high tide. On the right was my young son at the time play set. You can see some snow in the background. You can also see a rain gauge in the foreground, and I had 6 inches of snow and quite a bit of 6 inches of rain and quite a bit of snow on the ground when the storm hit. So not only you had the 6 inches of rain, but you also had the runoff of the snow. So you can see the patches still left. So quite a bit of water is just pouring in the ocean. So again, in Old Orchard in Ocean Park on a sunny day, red flag day. That's Ocean Park on a sunny day. This is during the Patriot Day storm, the same library, and a couple feet of ocean water. So the corner of Route 9, King Highway, and Temple Ave, and this is Old Orchard as well. And there's a car coming through, and we're supposed to learn turn around, don't drown, but apparently this, I see he stopped at the stop sign though, there's no wait. So did he flood away or did he keep going? He drove away. This is the Darwin Award, I think, thing we're going on here. So, and then again, Route 9 in Old Orchard. Quite a bit of flooding down there, which tends to flood quite a bit actually. So this is a combination, actually this Sandy's impacts. I have a bunch of photos of Sandy. This is actually still from the Patriot Day storm. And several homes down there were washed out to sea, an automobile in Saco as well. I should probably check the garage when we get home. But, so these are actually from the Patriot Day storm. Again, a lot of freshwater flooding. This tends to be forgotten. Very, very high waters on area rivers, a lot of river flooding. Category 2 wind damage, hurricane-like damage. Winds over 80 miles an hour in some spots. The buoys were showing that as well. A lot of trees down in the area. So just at that time, the reverse 911 started being employed, and that's when instead of people calling 911, police department calls you, and that was used for the first time in Saco. They've since then gone with a code red procedure, which I'm not that familiar with. But at the time of the Patriot Day storm, they were calling people to get out. And when we start talking about erosion and infrastructure loss, it's this type of damage. This is a local roadway on the beach, and it's same here as well. And the amount of erosion in one storm is incredible. And I'll show you how we're measuring the state of the beach before storm, then the state of the beach immediately after storm in a little bit here. But there's quite a bit of erosion in some places. And this must be not too far down the street, but we're looking at downtown Portland, and still quite a bit of water, 1 to 2 feet of water, salt water on the area roads. Cleaning Commercial Street, which needs to be cleaned by flood every once in a while, because God knows what's on there after a few years at a time. It's nature's way. So area lighthouses and homes took a beating. Like I said, 32-foot waves. The perfect storm actually had 100-foot waves out by Sable Island in that area. So they can get higher. 32 is pretty big. We had inland flooding. This particular road, I believe, was in Scarborough, and there was a fatality because this was all covered in water, fresh water at the time, and somebody drove over that and through that. And of course, the car went in. So pretty dangerous stuff. There's also, even the marinas took a hard beating. The Coast Guard was trying to save some boats, and the Coast Guard had to be, helped as well. There's very low clouds. This shows the height of the clouds. One of the weather maps we use on when you come for the tour with a weather balloon, you'll be able to see all our computers that have all this stuff. But there were low clouds and rain for quite a while, so that really hampered the help and rescue operations that the Coast Guard was doing or attempting. Further south, not to forget New York and New Jersey, but quite a bit of damage down there. That was ground zero, and some of the storm surge values down there were around 9 feet, whereas in our area, they're running around 3 feet or so. And I'll show more of that later. And they also did quite a bit of money. All your tax dollars are going to Sandy, as a matter of fact. Before and after images of some streets, local infrastructure. It's the type of things that they do. So, the Patriot Day storm, while we're here today, it's too sunny for it, but we're here for it today. So, it's the 7th highest tide on record. The tide was higher than the perfect storm. Perfect storm had caused more damage because it had higher waves. We had 6 consecutive tide cycles where we had flooding, coastal flooding. 30-foot waves ripped the buoys off their moorings. You know about that. And the freshwater runoff really aggravated the flooding of estuaries and marshes down by Wells, down in Saco, down in Scarborough Marsh, those types of areas. So, I'll get back to that in a sec. So this is another thing we look at work. This is a computer model of our weather forecast. When you hear on the TV at night, computer models are showing this, computer models are showing that. This is an incredibly dazzling photo that you don't want to look at too hard, you'll get dizzy, but this is the type of computer models we look at. The upper left is the jet stream, and these are different layers of the atmosphere with moisture and all that. It's moving very quickly for you to tell. But down here is what you might see on TV in the Weather Channel at night, the low pressure system that caused the Patriot Day storm. It starts off the Carolinas, and it rapidly moves out to sea, and then it curls back into New York, and it intensifies. And the theme here is when these storms back in off the ocean, those are the ones that really cause a lot of storm surge and large waves. And I'll explain more about that later. But whenever you see one curling in, like Hurricane Joaquin was forecast to curl into this area from offshore, those are the ones to watch out for. These are the buoys. I work with the marine program a lot. These are all the buoys. A lot of them are Nirakus, some of them are NOAA, but there's 61 knots there, about 75-mile-an-hour winds coming in with heavy rain. This is what we call our station plot at work. So very, very long fetch of east-northeasterlies coming in off the Gulf of Maine, allowing the waves to build up and the water to pile up as it comes on shore. So it's a very slow-moving storm. So I said that if it curls in off the ocean, that's bad. Also, if it's a slow-moving storm, that's also bad news for us. And you can see the storm. This is a satellite photo, but it curls in and it stops right about over New York City. The visible satellite photo, infrared and visible right here, showing the same thing, clouds coming in off the ocean. And winds are the biggest driving force of storm surge and waves that we have up here. So the strong winds really caused a lot of issues. There's also something called the Ekman spiral, and that's where the fanciness of this conversation comes in. So the Ekman spiral is, you may already know, but it turns water to the right in the northern hemisphere. So if you picture northeasterly winds funneling down the coast of Maine, over time the water would pile up to the right. In other words, it would pile up on land. So if you have a slow-moving storm and it's there for a day or two, that type of effect, it's like the Coriolis effect. The water will slosh over to the right and pile up along the shoreline. So slow-moving storm, strong winds are bad. Coriolis force and whatnot causes an issue. Also the pressure of the storm. For every 30 millibars in drop, that's a big drop in intensity storm, the ocean will rise a foot. So if you have a big storm coming in, big nor'easter, ocean will rise a foot just from the pressure. And there's also the astronomical tides, which you have to deal with. In this particular case, the astronomical tides were pretty high already from the lunar cycle. It wasn't extreme. When we get the big one, it's going to be like last week when our tides were very, very large, and we had a small storm come in. When we have a big one come in with high astronomical tides, that's going to be the biggie. So this is our radar that we use at work, showing rain bands coming in. You're right about here, Portland, Maine, and this is the outline of Maine here. The yellows and oranges are very, very intense squall bands, very heavy rain pouring in off the Atlantic at a very fast rate as well. These shots are taken about every 6 minutes, and you can see these showers and thunderstorms racing in towards the coast. And very big lull in activity down by Long Island, New York. So you hear about Doppler radar quite a bit with tornadoes and monitoring storms. This is a Doppler radar shot from a nor'easter from our storm. And basically the blues and purples are hurricane force winds coming in towards the coast. The radar is right about here, right here. So the beam height is at a few thousand feet. So we're getting, 70, 80, 90 mile an hour winds on this image. It's not right on the ground though, it's at a couple thousand feet. Some of that heavy wind does mix down to the ground during these storms though, when you get the squalls that I showed in the last slide. So the impact of the Patriot State storm. Here it is, it's 13.28 feet, that's the height, but we also had big waves. So it was one of our higher impact storms we've ever had. There were others. There was the blizzard of 78. It was the highest impact storm. There was also a blizzard in January of 78. And what that did was it took a lot of the infrastructure away, moved a lot of boulders, been out of Fortune's rocks, a lot of the armor that they put along the beaches. It basically removed those. And then when the blizzard of 78 came in and hit, it devastated the region. So that was the worst one we've ever had. So 13.3 feet is about when we start getting Commercial Street flooded, not too far down the street here. So, and it did flood during this one. It was close enough. Getting a little bit out of my comfort zone, talking about beach morphology and what the Maine Geological Survey does. I'll just mention a couple things that they've done. They graded the state of the beaches right after the Patriot State storm to see how much erosion and dune loss was occurred with the storm itself. Some beaches fared pretty well. Willard Beach kind of protected A-. Wells Beach had an A, but Ferry Beach, Kinney Shores down the Saco, Scarborough Beach, and some of the other beaches that were exposed to the northeast and some of the waves did not fare well at all. So they are the experts in that. I am not. I will show more on beach erosion and whatnot, but they're definitely the experts. And going back and referencing a paper, Dolan and Davis, 1992, they classified storms into 1, 2, 3, 4, and 5 storms and how intense they were. And the Patriot State storm was probably 3 or 4, getting to significant and extreme category in terms of erosion. They've got all kinds of categories for that, which I will not get into as it's a little bit out of my comfort zone there. But I do know where I live down at Saco very well, and I do take measurements of sand loss down there and erosion. And it is an area of very rapidly deteriorating beaches. There are large geotubes. Those are large bags of sand, very large, about 15, 20 feet across, that they fill with sand and they put along and bury into the beaches to help keep the sand and infrastructure in the homes, which are right next to the water's edge, right there. Further down the beach, there's pristine, modestly unstable dune systems. So I'll show you what a pristine dune system looks like in a minute. One other thing from the Maine Geological Survey that I want to credit them to is probably some of you have seen this a few times, but this is a map of the shoreline of Saco, and it's changed over the years. So this was last done a few years back, I think 95, but in certain years, the shoreline has changed. It's really receding inward over time. So these little rectangles are actually people's lots that are now underwater. And so they say, I've heard that some people are still paying taxes on those lots, so if it's ever recovered, you could do that. But it's a very interesting way, and I wish they would go back and do a current one. And you see that the roads, the shoreline roads there, have gone over the years. It's just an amazing way of showing that. Here is one of them, Sur Street in Saco. And when I said pristine dune heads, this is more, when I say pristine, there's no geotubes, there's no armor, there's no boulders put there from mankind. No, it's just dune grass and natural sand. And over the storms, they keep planting these green vegetation here to help build up the sand dunes, but you get one storm and a lot of it just rips out, and this is what you get. So they're thinking about removing this road, Surf Street in Saco. I don't know what the latest is on that, but that's how fast things are changing down there. Here's a closer shot of one of the geotubes. This is during a recent storm, February 8th of this year. We had a lot of minor and moderate storms this winter. Not too damaging, but still enough. But they pile sand on top of this several feet deep before a storm, and it just takes a few waves to kick it off. And so, I mean, you can see how close these homes are from getting hit by waves and more erosion. To help with that, we worked with several groups to get a tide gauge down at Saco. It's down at the end of the pier. It's from some Sandy supplemental funds that we were able to obtain, and it's there for a host of reasons. Most of them was what I just showed you. It also helps support wave models that are being developed by the University of Maine and other groups for the Saco Bay area, and maybe expanded to Casco Bay, to help us learn how the model is verifying, how is it working out with time. So that's very helpful. So I said we were here today to really focus on the waves. Now I'm going to really focus on the wave part and not the water level part. And some of the coastal hazards, large ocean waves produce coastal erosion and coastal flooding. So here's an example of well, to put the two in perspective, you can't have a talk without having a sea level rise chart on the front. But when I talk about waves, I'm going to talk about splash over and overwash quite a bit. When I say splash over and overwash, this is what I mean. This is happens to be a barrier, Jersey barrier right here. But splash over is when waves are jumping over those barriers and causing erosion or other effects to people's properties, private and public properties. One other thing it does is if you have a low spot on this side of the dune, it fills up with water too. So it not only causes erosion, but it just makes for a lot of deep water in places. So, to focus on what's important about waves, I want to use the Patriot State storm. Here's a paradox. Okay, this is right in downtown Saco again. Sorry where I live, so I get all the pictures there. But this is the top of a mailbox, and water. This is inundation, coastal flooding. All right. When the water receded, there was actually very little damage to some of these area homes. The water went out, low tide, and everything was fine. But just down the beach towards, close to the beach, maybe 100 yards, this is where the beach is. And these are the homes that were affected. So these homes were affected by large battering waves, whereas the other homes were inundated. That's not a good thing. They tell us with social science classes and all that, picture a 5-year-old out in the elements. It's deep water. It's going to be a problem. Inundation is not a good thing, but the effects of large battering waves is what we're going to focus on, because it ultimately does most of the damage to infrastructure. So years ago, about 10 years ago, right when the Patriot Day storm hit, I did a project in our office where I related storm tide, the height of the water in Portland, with the wave height at offshore buoys, and tried to come up with, well, what type of damage are you getting? And it ended up being the obvious that the higher the storm tide and the bigger the waves, these red dots start appearing over here. That's where you get the major damage. So there definitely was a correlation with the height of the waves causing damage. And actually, there was a correlation of freshwater runoff, too. If you have very heavy rainfall, you could have flooding that occurred below flood stage in Portland. That's with the help with NIRCUS. They're very helpful with us and certain projects and all that. And this is their network of buoys and other things that they put in the water to measure salinity and waves and all kinds of neat stuff. So large waves combined with high storm tides lead to coastal flooding and damage. So I wish I could say this is Higgins Beach, but it's Hawaii. It's a pretty picture of Hawaii. So to have large battering waves, you need wind, You need fetch, which is the length of ocean that the high winds are going over, and duration. That's how you get the big sea states. So increased wind speeds allow for, that's the first one I said, allow for wave growth. So when you get this intense East Coast cyclogenesis I was telling you about, the bombing, the very deepening low pressure systems, the intense nor'easters, and hybrid storms. Hybrid storms tend to get us, not the pure tropical, we don't usually get those, but you get these half tropical, half nor'easter ones that cause a lot of problems. They allow for wave growth. This is a picture, this is actually an intense nor'easter in the right in the middle of winter. I think that was January, February, and I had an eye to it. So some of the stronger nor'easters can have an eyes to it. And they're really triggered by the Gulf Stream waters coming up the coast. 80-degree waters in the summer, or actually higher, and still warm waters in the winter. That helps really trigger these big storms. And when you get the high winds going over the water, if you have 30 knots of wind, you will impinge this amount of energy on the water to create ocean waves. But it's really exponential. When you get 40 knots of wind over the water, this is the amount of energy that you're putting into ocean sea states. So when you get into larger storms, it really gets intense energy that's over the ocean very quickly. Fetch is the second thing I mentioned about large battering wave growth. And fetch is the length of time. Now in the Patriot State storm, we had an east-northeast flow, so it was pretty much unimpinged flow over the ocean waters to the coast of Maine. That's a perfect direction for if you want large waves. Moving fetch, we rarely get here. It's more of a West Coast phenomenon. A moving fetch is when you have an intense area of low pressure and strong winds heading towards the coast. And what happens is the wind and the waves kind of resonate with each other as they come in to the beach. In other words, the low pressure system is moving at the same speed as the wave train. So the wave train just kind of builds up, builds up, and builds up because the highest winds stay over the same area for such a long period of time. That's called a moving fetch, and that happens on the West Coast a lot. It did happen in this storm as the low, remember I said when the low backs in, it's bad from the ocean? It's because that moving fetch, those high winds move at the same speed as the waves and keeps building them up. And here's an example of how that happened in the Patriot State storm. Portland's here, you're off the mid-Atlantic coast. This is the end of the loop. At the beginning of the loop, the storm is well out to sea, kind of like Sandy, and it barrels in towards the coast. And so you're getting all these waves moving, resonating as they move inland. And this occurred during February 2010 nor'easter. You can say that the nor'easter's getting closer, the winds are getting stronger, so this is wave growth. This is the height of the wave with time. So the waves are growing and growing and growing, and all of a sudden, right at about high tide, you get this 10-foot jump in wave height. That's that wave train that's coming in and resonating with the low pressure system as it comes in. So it can have a really big effect, and you can see the steady state increase and all of a sudden this jump. Here's from that February storm some examples of some of the erosion. There's that geotube again in Saco. And I said sometimes the landward side, when you get the splashover going over, you can flood areas that are lower in landward areas. That's the flooding that's occurring. I believe this is Wells Beach, and this is in Popham, where they tell me when they lose trees due to erosion, they tie them to the sand dunes to help build up the sand again in the area. And then duration is the last thing that creates big storms. Now, you want a long period storm. The perfect storm is a great example of that. It sat off the coast for days and days and days. And you start to get these very, very large waves, a full sea state when that happens. Fast-moving storms, usually the waves are not nearly as high. This is Hurricane Bob for people who are in this area, Portland, back in those days. No issues with coastal flooding and erosion. The storm went over the Cape Cod Canal and barreled into the Gulf of Maine. By the time it reached the Gulf of Maine, they didn't have a chance to really build over much in the way of waves. It was only in the Gulf of Maine for 8 hours, and it's just not enough time to build the sea state. So when we bring it all together, and we're thinking about large battering waves, a slow-moving storm that's backing in off the ocean, similar to the February 2010 one, and a strong, persistent moving fetch coming in. And this particular storm, we had some of the highest wind gusts ever reported in southeast New Hampshire and York County in Maine. And that's where you get the really, really, really big coastal erosion events. This happened to hit at low tide, so we got lucky. So a few final thoughts about large waves. Waves coming into the beach. There's something called wave setup. Excuse me. And that's the increase in water levels just due to the waves continually pounding onto the beaches and bringing up the water level. Excuse me. It's about 10 to 15% of the wave breaking height. And last of all, there's wave run-up, and that leads to splashover. We have this infinite number of waves, but the largest of the waves are the ones that shoot debris, stones, seaweed that plow operators have to go out in some towns and actually plow the roads after a storm. The wave run-up, the largest of the waves, sends these obstacles up the beach. Bathymetry plays a role. If you have a very steep beach, you tend to have more erosion. A very soft sloping beach like Goose Rocks Beach or Willard Beach, something like that, would be less erosion effects. So orientation of the beach and bathymetry play a role. I showed you that. Very long period waves cause problems. Hurricane Bill was around in 2009. They had to do a whole bunch of rescues. About 10 people were washed out to sea, and they brought the Coast Guard in with copters and all that. There were kids in the water, and they fetched them out. They were at Acadia National Park near Woods Thunderhole, and very large breaking waves there. So long period waves from hurricanes that are far off the coast can cause some issues as well. Then you have very, very long period waves. We had what we call a meteor tsunami, an actual tsunami in Boothby Harbor in 2008. And when the tide was supposed to be going out, it was coming in and vice versa, and there was some damage to docks and whatnot that occurred. What happened was, again, that resonating thing comes up again. These individual squalls were moving north at 80 knots over the ocean. You're looking at another radar picture. This is heavy rain squalls. And it just so happens that a squall moving north at 80 knots through the Gulf of Maine is also the same speed as a deep water wave in the Gulf of Maine. So it built up these waves, and they crashed into Boothby Harbor. So when people say you can't have a tsunami in Maine because you're protected by Georges Bank and all that, because it'll break in the bank, well, if it forms in the Gulf of Maine, you could be in trouble. So, and then there's a very, very large waves, the Sumatra earthquake in 2004. So with waves and erosion, one of the things we wanted to work on was is called wave run-up. How far up the beach will a wave travel and cause erosion to infrastructure? So to do that, you need to know what the height of the tide is. You need to know the storm surge, the extra water due to the winds. You need to know the extra water due to the wave setup. That's the water that the breaking waves are adding on along the beach. And you need to know how far the wave bore is going to travel up the beach. And you want to know if it's going to hit a sand dune or home or something like that. So you have to take all those things into order. And to do that, you really have to focus quite a bit more on the wave setup and run-up. So that's what we'll be focusing on. This is that big nasty equation that I showed just for fanciness, but I'm not going to go through that. But basically, we're working with the USGS on an empirical model, a collision model, that takes into account not only wave height, but wave period. Those big ocean waves I just showed you, the meteor tsunami and the Sumatra waves, they have very long period waves, so they can travel very far inland. A long period wave has a disproportionate amount of energy than a wind wave will. So in this project we're doing, we're trying to forecast whether if you get your storm surge, you got your still water level here, storm surge, and your wave run-up, will it impinge on the dune system? And if we run that big long equation, and we know the height of the dune, the height of the base of the dune and the top of the dune, and we know the wave height and the wavelength, we can forecast this now. So it's kind of uncharted territory we're on. In this particular case, if the wave ends here, we're not going to have any problem. Green light, everything's a go. If we have larger waves, we're getting in the collision regime. That means we'll have some splashover and some erosion of the dunes. The height of the waves and the wavelength are sufficient that we're gonna get that from this equation. And if we have waves toppling over the dune, we're going to have splashover. We're also going to have that backwater flooding I showed you. If you're on the lower side of the dune, it'll start to flood roads in there. And if the still water level is going over the dune, you're in a lot of trouble because the whole ocean is inundating your area. So that's what we're trying to forecast. So we've kind of come a long ways. I worked with Riley and Ian, Riley Morris, and a few others at the Gulf of Maine Research Institute about 10 years ago, and we came up with this forecast scheme This is water level on this axis and wave height on this axis for the Patriot State storm. And you're actually looking at an hour-by-hour forecast of when there's going to be damage, because when it hits this yellow and red, we start to have damage to infrastructure. And you're actually watching the tide go out hour by hour, and you're looking at, again, water level and wave height. And you can see right now we're starting to get some damage along the coast. And this was the first done at its time 10 years ago. It's a kind of a graphical way of seeing whether or not you're going to get erosion. And then it kind of evolved to matrices. I know it's hard for you to see, for our office where I have water level and wave matrices, and it actually tells our forecasters what type of product to put out, a flood advisory, flood warning, that type of thing. And now we're working with the USGS on this wave prediction model. It's further evolved with GMRI, a plug for GMRI. Ian and others have worked towards putting this on the web. This is now available on the web, and I can get you the address for it later, but you can set it up and it'll tell you if it's going to hit the dunes or not, what waves or not. So this is all available online. And again, we're really pushing the envelope because we're looking at meteorology, which my peers would say I'm not good at anyway. And then you're throwing in oceanography, which we took one course in college on that. And then you throw in a little social science and a little geography that the Maine Geological Survey is doing, and you're throwing a lot of potential errors in there. But we are learning and we're moving along. We work a lot with emergency managers on hot spots along the coast. These are spots that we surveyed the dunes. This happens to be Biddeford, the Biddeford emergency manager. These are high-risk areas where we measured the slope of the beach, so we know how fast those long-period waves are going to ride up the beach, and also the base of the dune system and the top of the dune system. Or in this case, a lot of times it's not a pure dune system. There's obstacles in the way. So that's what we throw in our equations, and we see if we're going to get erosion. These are our hot spots in Maine and New Hampshire. Definitely down in Saco, Biddeford, Hampton is one of them. Very problematic. Plum Island in Massachusetts. They've been filling in around here as well. And that grid you're seeing is a new computer model that we're going to be running with another group that gives us a very high resolution as we get in towards the coast. Okay, so let's see how good these, or poorly, these wave run-up forecasts work. This is actually a hindcast. This is something that we ran after the fact to see how the model worked. We knew the wave height and wavelength and all that. This is from Saco. In fact, we had just been down there the week before taking measurements, and there they are with knowing a storm's coming in. They've got crews in there building up the sand. This is at Camp Ellis Beach. So we had, this is December 27th. This is a big year. This was the year of 3 large storms. So we had 21 to 25 foot seas, and we only had an astronomical, and those are reported by buoys off Ogunquit, and we had an astronomical tide of 9.5 feet. That's actually pretty low for Portland. It's usually not a problem. But we had a storm surge of 2.5 feet, so that we reached 12 feet flood stage in Portland. On a sunny day, even the other night with those big tides, if there's not much in the way in waves, we don't hear about it much. Not a big problem with infrastructure. But in this case, it was, they were live down at Old Orchard Beach, and it was forecasting erosion and overwash. I'm sorry, that's a little hard to see. And again, these are where those overwash and erosion pictures came from. That's what you're looking at, overwash and flooding. So that seemed to work out pretty well if you have somebody willing to stand in water and cold water and take pictures for you. January 3rd, 2014 was an interesting coastal flood because it was below zero. And usually you don't get a storm when it's below zero because a storm it's bringing warm air off the ocean. That's what helps create a storm. You're overriding warm air over cold air. Well, this one was below zero, and this is down in Hampton. And not only did it flood, you get coastal flooding by the large waves and whatnot, but the fresh snowpack that you had a foot of snow the night before, it held in the ocean water. So when the tide went out, you still had all these streets, and you think the snow would melt right away, but there's a little lag there. It just sits in ponds in the area. Hampton is a really tough area for coastal flooding. So tough to see, but erosion overwash were predicted. Did well in some areas, not well in others, and this is the type of thing we had that day. In fact, there's a little bit of ice forming here. A lot of ice formed in this particular storm. This is along the seawall on the strip in Hampton on Route 1A. And you can see it really filling up that road. These are more pictures from that storm. It was a survey I was able to do with the Saco emergency manager. And when we do that, we do get access to closed roadways. We don't ruin our cars, we ruin somebody else's. And it gives us real-time feedback to the forecasters at work. I can call into them and tell them what's going on in real time. And it was below zero. These are boulders that are just covered in ice. The ocean's just this big sloshy pit, and a lot of ice formed for that particular storm. So getting to Sandy, doing a wave run-up hindcast. Big waves, big tide, big waves. Erosion and overwash is expected. I wouldn't recommend this. This is on the Route 1A again in Hampton. Couple enjoying a nice quiet day in the ocean. And so that's the type of splashover and whatnot we had. That wall is pretty high in Hampton. I don't know if you've seen it or been down there. And it's curved as well, so the waves are designed to kick back to the ocean. But I guess if you get a big enough wave, it doesn't matter. And in the backwater area of Hampton, we do get houses surrounded by water quite a bit. Okay, back to Hurricane Sandy. Why was Sandy so unique? Why are the waves so big? We had this is up at jet stream level. We had this big high pressure system driving the storm towards the east coast. There were other storms out to sea. I've been told by an old salt professor from Albany, University of Albany in New York, that if you see a big storm way out here, look for a big storm on the east coast. And certainly that did happen in this case. The track was over very warm water. It was very tropical for a very long time before it kicked into parts of New Jersey. But even the influence here in Maine, the crews coming out having to plow seaweed, why not? It's Maine. So it went right over the Gulf Stream. 11 hours before landfall, it still had an eye, and it's still heading towards the shoreline. Now, this is where, as forecasters, a few days out, what do we do with this type of information? These are storm tracks for Sandy. So do we say the Azores in Spain, where our buoy's lost, is going to get crushed? Or what do we do? And I'll be talking more about that in a minute. It has to do a lot about risk communication and decision support services that we're getting more and more into. How do we best show the public and emergency managers confidence levels and where the storm is going to meet up along the ocean or along the shoreline? And for this particular storm, for Sandy, it was very difficult. These are computer models 3 to 4 days out. Okay, this is Portland, Maine right here. Portland, Maine right here, showing basically a landfall over Portland, Maine. So if that had happened, that would have been devastating. Everything you saw in New Jersey would have happened up here. So can it happen up here? Our computer models say yes. Did it in this case? No. Has it threatened since? Yes. Hurricane Joaquin was forecast to make landfall up here a few days in advance. That didn't in that case either, but we were getting close to having the big one. But this is how it was expressed, showing areas of uncertainty. Rainfall and flooding was pretty heavy up here and also down south, and heavy rainfall tends to fall to the left of the track of landfall and tropical cyclones. I don't have time to get into that now, but that's why the heaviest rain was just the left of the track, south of the track. Getting off topic a little bit, but to share something modestly interesting, Sandy's cyclone phase. Sandy was a very pure, warm core symmetric storm, and this is what this deep red shows. And if you're a raging nor'easter in the winter, you're over here. This storm had characteristics of a warm core storm all the way just about to landfall when it reached New Jersey, which is pretty highly unusual for that far north and that far late in the season. Why is a cyclone, I went through that awfully fast and I'm sorry, but why is the cyclone phase important to us meteorologists? Because storm intensity and predictability are a function of the storm phase. If you're a tropical storm, you're less predictable by nature than you are when the jet stream connects to it and steers it into areas in the northeast. So that's why we care about that. So going to the beach morphology piece of this, the verification of our models and whatnot, we have wave run-up verification, storm-based beach survey profiling teams that's sponsored by Maine Sea Grant, Maine Geological Survey, and the Wells Reserve. And these are volunteers that go out once a month and actually take these rods and measure the slope of the beach and the dune systems every month. And you can get a feeling of how the beaches are changing. Well, we ask people to do this immediately before and immediately after a storm, such as Sandy. The reason being is sometimes the beach will naturally replenish itself with time. So even though you had all this erosion and all that, a month later or so, most of the beach may be back to its natural state. It may not, but it may be. We wanted to capture immediately before and after a storm so we could quantify for the first time ever how much sand is being lost during a particular storm. So we did this for Hurricane Sandy. We asked a couple volunteers to go out, which is not easy because there's still breaking waves, right before and after a storm. And immediately before a storm in blue, you're looking at beach profile, you're looking at the top of the beach, and you're measuring the sand coming down the beach to the water here. And that's what the beach profile was immediately before the storm hit. Immediately after the storm hit was in red right here. And that's about 1 meter loss in sand throughout the entire beach system. This happens to be Wells Beach. So quite a bit of erosion was measured immediately before and immediately after the storm. A note about beach erosion, however, the geologists tell me, because I'm not an expert in that field, we had a blizzard of 2013 a few years ago. That's where Portland had its biggest snowfall ever, about 32 inches. And the winds were actually northwest during that storm, and we actually had waves bring in sand. So a northwest wind will do that. It may eat away at sand towards the lower end of the beach, but it could actually build up the dunes. It did so in this case. It built up the dune systems. It also lower down the beach. It also exposed 3,000 to 4,000-year-old stumps. I guess there used to be a forest in Gooch's Beach. Who would have known? That's been, and it's still buried in the sands. They're still underneath there. So, and this was the profile. There was loss where those stumps were shown. There were actually gains near the top of the beach. Here's an example of it. This is Saco, where an actual road filled up. These waves with the northwest wind actually brought in all the sand. It's quite a bit difference. I mean, they had to plow out. They had to dig out this road right after the storm, just so people could pass through. Heavy rainfall also plays. I touched on that earlier. Very heavy rain with the fresh water coming out of the marshes, and the incoming salt water plays a role. Here's a storm in September 2015 where we had 6, 7, 8 inches of rain during a full moon, during the blue moon. And this is parts of Portland. This is the Bayside area, I believe, and incoming water through the sewer systems up through the drains that just couldn't take it, and incoming salt water. I spoke to some of the police and emergency managers about that, but pretty interesting things happening down here. Large waves can change the positions of the beach, how steep the beach is, and where the steepness of the beach is, and where the sandbars are. So it really can affect rip currents quite a bit. We're trying to expand our rip current program for the summertime. And just finishing up here, verification. We use anything we can to verify our storms, emergency managers, social media more and more, cameras quite a bit, ham operators, which is what this gentleman's doing, police departments, public, and the dune profiling teams. So we use quite a bit of things. And to finish up here, also we really are focusing on decision support services. This happens to be during Hurricane Joaquin as the storm was heading up the coast. And this is an example of how some of the tables we would use to issue an emergency manager slide briefing twice a day from our office. We put all kinds of information on it that goes out to them on a daily basis. We also put it in our weather discussions, our area forecast discussions. Could be some erosion and flooding in your area. And when hopefully we send that out ahead of time. Sometimes we don't, sometimes we do. Hopefully, if we do, there's action taken. In this particular case, in Saco, reverse 911, there's also a citizen emergency response team they have, and they get people to sandbag and block traffic in direct areas before the storm hits. That's the goal anyways. So, and just a final few words here on social science, which I touched on earlier, and the fact that Sandy was supposed to come up this far north. Messaging is a big, kind of a big new focus area for us. We're all scientists, but we didn't take many social science classes in college. So this is fairly new, but we need to understand and work with the public more that category gets a very big level of attention, especially with hurricanes. There's lots of false experience with hurricanes that sometimes people think they were in the center of the storm and they weren't, vice versa. So when we work towards getting somebody to evacuate, and in this example, when I went down to the Hurricane Center, it was with storm surge, but you could use it with large battering waves or any type of, the great thunder and lightning and hail show you had last night. You could use it for that too. There's the cognitive part of people's brains where people have knowledge about hurricanes, forecasts, and storm surge and whatnot. They have a little bit of background thoughts on it. But then there's also the affective part, the feelings of how people are going to react to a storm coming in. We need to arouse emotions on occasion, not too much on occasion though, with folks to connect with that part of the brain. And there's also the social part. What are my neighbors doing? Why are they boarding up? Why is that? And what it all does is it gives a world view, world traits of the world. People seek safety, or sometimes they're very risk averse. So people react in different ways. And people need to know that the danger is real, and that's one of the things I try to do at work was try not to overwarn. I know we get some of that. But know how to respond, have the resources to respond. With Katrina, a lot of people did not have the resources. And so we're running models, we're working with the University of Maine at Orono, and we're just starting a project with some folks, also at UMaine Orono, on modeling Saco Bay. So I think that's it. Thank you for your time. This is the type of storm that we have to worry about, something like Joaquin, where it's going to come back in and curl back in from the ocean, open ocean waters. So thank you very much, and stay tuned.
Questions?
Okay. Yeah. Yes.
Would rising sea levels increase the damage by a smaller storm?
It would. It would do that. An increasingly smaller storm, as a matter of fact, yes. And that shows up every time we have high astronomical tides, and so that's essentially you're raising the sea level for a few hours there, and we get more damage inland. So definitely, yes. Yeah. Yes.
When you talk about wave height, I'm assuming that's like peak to trough, and
That's right.
It might be out in 100 feet of water, but how does the morphology of a wave change when it's actually about to crash? What would a 30-foot wave look like as it crashes?
That's a great question, because we don't know what the wave height is at the beach, because we don't have anything to measure it with, and somebody would steal the buoy anyways, a surfer, or maybe me or whatever from my back pond. So that's a great question. So what we have to do is take beaches 3 miles off of Gunquit, the Portland buoy 3 miles out, and make assumptions as the waves are coming in. So the waves are 30 feet out there, and this is the corresponding damage we're getting here. And it's called the empirical way to do it. That's the only way we can do it. Maybe somebody someday will get $1 million and a little Jacques Cousteau to float over some buoys or something. But that's a great question. We don't know what the wave height. We have these equations where we can assume what they're doing, but we don't know, and we can't measure them. So we have to use what's out there. And a lot of times you get these sandbars or protective systems where you may have a 30-foot wave out there and Old Orchard's getting crushed, but a southeast-facing Hills Beach is not. So it's a great question. Yeah. Yes.
I noticed we should take that first slide, the center of the low is 976 millibars.
Yes, you caught that. It's tiny font. Yes.
Yeah, well, I was curious, compared to the perfect storm, was that lower? Or?
Perfect storm was quite a bit lower. That was more like the 38 hurricane. Many millibars lower. See if I can remember. Intersection of Hurricane Grace, a nor'easter, and another piece of energy that I can't remember, but it dropped it down to, I know most people are used to using inches of mercury here. Probably 27, 28 inches of mercury, but 930 millibars of intense hurricane. Yeah. Yes?
In several of the hurricanes that were predicted recently, they talk about the U.S. model or the European
Yes.
model.
Yes.
What causes that differentiation?
Are we still on camera? Let me get this thing off. It's the physics package used with the European model is preferred in many ways, especially with maritime storms. And we're trying to get the American model to mimic that, and we've been told that we're right up there with it. I still think we're working on that, so that's my best way I can answer that. So we got a ways to go. It has to do with the physics packages they put into it and who decides that and what type of storms that the country really wants to focus on. I guess in Europe, all the storms are coming in off the ocean, right? So they want the maritime feeling model to do better. Yes?
Have you ever tried to run your models relative to the FEMA models in predicting damage?
I have not. That would be interesting to try.
Given the controversy out there about the FEMA model.
There's a lot of controversy, yes.
You're doing the same thing they're doing.
Yes.
It'd be nice to know if they're
Yeah.
as far apart as the European and American.
Right, right. I try to stay focused more on the waves and not the water level height, which I know they focus on, but I know there was a lot of people who called our office when the FEMA maps were being redrawn for Portland, and I don't want to get into this much because I don't want to have tomatoes thrown at me from anybody. But Portland Harbor is a harbor for a reason. So the waves are cut down because it's a harbor. So that's why they call it a harbor. So that probably went over a lot of people's heads if you weren't following with the newspapers articles and all that. But I'll leave it at that.
But it'd be nice to see you run
It would be interesting. It would be interesting. Yes.
how close you are.
Yeah.
Okay, one more question? and we're
Yes.
Our standard, southerly, southwesterly onshore breezes in the summer, fair weather.
Mm-hmm.
Can you ever get big waves developed out of that, or is it just too short duration?
You can. It's tough in the winter because the southwesterly wind is usually warm air and it skips over the water. It's kind of like cold air is like molasses. So when you have southwesterly winds in the winter, it kind of skips over the top of it, so it's not that windy. But in the summer, southwesterly winds, sure, especially if you're down east, you get very large waves. Very large waves. The fetch length is not that long, so you get 10 to 15 footers down by Acadia and whatnot. Yeah.
Great, well, John, thank
Okay.
you very much.
Thank you. Thanks for coming, everybody. It's way too nice out to be here. And if somebody wants to chat after, we'll go outside in the nice weather. Thank you.
Thank you.
Well, I make bread too. I just made all this up. I don't either. No kidding. I've got pictures down there during the hurricane. Yeah. Wow. That's a great question.
It is?
Yes.
Because it's my son who just asked a great question.
Nobody knows it's called Mother Nature. Waves will naturally parse themselves. They'll separate themselves out of